why do we care about vibrations? And there are multiple reasons or examples I want to motivate the whole topic here. So, for example, Tacoma Narrows Bridge is always an example. We in vibration engineering or structural. This is a structural engineering topic we like to bring up. And so it was a bridge. It was opened in the 40s, and a brand new building and the bridge. I mean, we have all crossed bridges all in our life, and they tend to be, they're supposed to be very solid structures. But I'm going to show you what happened. Where are we? So you could see that here. Yeah. So here there's maybe you can see it a little better. Can I make it big? Yeah. So here that's a car. There's a couple of pixels there, and you can see that the bridge is like kind of torsion. And what happened is believed that the wind came from the side here, and there's an interaction of the wind and the torsional mode of the bridge. And if on a certain wind condition, there was believed that there is some sort of resonance and give rise to these strong vibrations, and the bridge actually collapsed. Unfortunately, we don't have the collapse of the whole thing on here. I should probably bring along a different building, another video, but I think you can see the collapse of the thing online. So yeah, you can see here that that's the collapse of the bridge. It was a brand new bridge. I don't know how long it was there, maybe a couple of weeks, a couple of months. So in the 40s, Tacoma Narrows Bridge. I think it was Washington, but I'm not entirely sure. And it was a big thing because it was a lot of money, and it was supposed to last for decades, and it didn't really last. And there's still an academic debate about what the real causes are, but we can see something is vibrating, and the bridge should not vibrate. So that's a problem there. And this course hopefully brings you there to understand a little bit more what went on there. Similarly, a thing is a mass imbalance. So in many applications we have rotations. So like a lot of engines, be it combustion engines or electric engines, they rely on rotations. And if rotations, ideally your masses are centered, but it's not going to be ideally the case. It's not always going to be the case. So your the weight of the mass of the rotor, whatever you are spinning, is going to be off center, and that causes classically vibrations. So here, this is, for example, I think this is part of a gas turbine, and you can see like how many million or whatever there are a lot of blades, and how many parts are on the thing, and you need to kind of correctly balance the whole thing. Otherwise, you're going to see some sort of vibration, and this is very tricky for such large systems. Another thing where you have is, for example, in your tires. I don't know, I haven't looked at my car. Probably should have a closer look. But you can balance your tires. And what they partly do, I haven't seen that. I haven't looked, but my car has some weights, so they can attach certain weights to balance your wheel, because the wheel is also spinning. And if the spinning is too large, if the unbalance is too large, you're going to see it's going to have impact on the suspension, which is not good. Anybody brought his car to the shop and got unbalanced the tires? Anybody familiar with that concept? You've done that. So you have this weights here, or you don't know? They do something.
I don't know. They do something. I drop it off and I leave and I come back and pick it up.
And you pay for it.
Yeah.
All right, it's the same. I don't know what they do, but I believe them. Similarly here, one thing what is happening, or what is common in these crankshafts here. So this is the classical combustion engine, where here are the cylinders to the engine are attached here, and because they need to be off the center, there's an art of kind of counterbalancing this off-centricity with so-called counterweights, just to ensure that the axis, the center of gravity is in the center of rotation. And that's a whole art. Who knows how long we still use combustion engines, but it is important in these applications. And just to show you a little bit what you shouldn't do, all right, we're gonna have some sound, I guess, now again.
All right, it's about to rain, but not gonna let that
So this
spoil.
is somebody
Something a little heavier.
with his. Yeah, please don't do that at home. So he's just throwing a weight in the washing machine. What he wants to do. Serial number. All right. Okay. Let's go to other applications here. Then you have an important topic in for aerospace. I mean, we all have most of us probably have flown in an airplane, and so no, I don't want to vote. So this is now a glider, and you can see here the wings. I've never been in this condition. I have never been on a glider, but I mean, it doesn't look safe to me, and I was told that this is pretty detrimental. So we kind of want to avoid these conditions. Here again, here we have an interaction between the air and some structure mode of the glider, the airspan. I'm not going to talk about the fluid dynamics in this course. I'm going to only talk about the airspan, and that's it. And if we understand that, what's going on, that's the first point. And if you want to understand the whole thing, you should probably take a fluid dynamics course, and then maybe you can put them all together and solve this problem. As far as I know, this is still an ongoing problem. Gliders, I don't know, maybe for gliders, I don't know if it's still a glider problem, but I know that there's still ongoing research in because you want to operate those in various conditions. A lot of things might happen there. Similarly, power lines. Show me some power lines. Power lines, there are power lines. This might be Wisconsin, I don't know. Could be from the scenery or maybe not. Probably. Anybody recognizes the scenery here? It's pretty remarkable, though. Yeah, but you can see those lines moving. I haven't seen that. I haven't really watched out too much, but I haven't seen the strong movements of those kind of cables. But you can see, you can picture that this is a problem. Those cables are usually not designed to do that, and when I've seen power lines, usually they're pretty static, just hanging in the air, and that's it. But in certain conditions, we can have those kind of thing, and this is somehow a little similar. I am going to play the video again. This is again a little similar to the Tacoma Narrows Bridge, where the wind was the driving force, or some people say the wind is the driving force. So what's happened here? Here's a bit better understood. I can just right, we're here. Why can I insert space? Oh, I don't know. Okay, well, never mind. I'll just draw. So what happens here for the galloping is now you have like let's say, so this is a cross section of your cable, and the problem is it happens usually during winter. So and what you have in winter, especially in Wisconsin and similar areas, ice. So you have wet conditions, and then in these wet conditions, the moisture freezes, and then of course this thing forms an icicle essentially. So you're gonna have some kind of like icicle, something like that. And now if the wind is correct, and now we have a wind blowing from, let's say, from this side, you can already see that this structure, so here, acts like kind of an airfoil, and this is going to have a moment on this cable, and this wants to, let's say, I'm gonna make it in this color, wants to twist it maybe like this. So it has a moment. So we see this is already some movement, and if you have it in this direction, you have lift. It can create a lift on the whole cable. And so you have an interaction again of the wind and the cable, and this of the more solid structure part, and this again gives rise to detrimental vibrations. And this can lead to power outages in many cases. It can lead to power outages. I thought I had another structure. Let me see if I have that. Anybody been to London? London? Maybe? All right, some people have been to London. No, I don't have it on here. Okay, anyways. So there's a similar situation with the bridges happened in London, the Millennium Bridge. Anybody heard or knew about the Millennium Bridge? So some people. So when they open up the, you can Google, just Google yourself. Essentially, when they opened up the bridge and to the people, they noticed that the bridge began to sway, and that was not well designed, and they put in a lot of. Afterwards, they had to redesign the bridge, include dampers and so on to finally get this bridge then open to the public. Now you can pass the Millennium Bridge. I guess some people might have. I think I probably did. I don't remember anymore if I did or not. When I've been to London, and this was apparently, so some people say that there is a tendency that when a lot of people move along a bridge, and this bridge begins to sway, that unconsciously you kind of synchronize your steps with your neighbor, and the neighbor with his neighbor, and so on. So essentially, what you have then that. You have a synchronization phenomena in the crowd of people passing the bridge. And this gives rise to certain frequencies and an excitation which is not good for the bridge. And in the case of the London Millennium Bridge, this had led to vibrations, noticeable vibrations, and they had to redesign the whole thing. Was in several newscasts placed. I thought I had a BBC one. But apparently didn't make it in the final sets of slides. But Millennium Bridge, I can post a link somewhere, or you can just Google it yourself. Yeah, that's always also a good big thing. All right, let's move on. Timekeeping is another application of vibrations. So the first clocks, or not the first clocks, but the first clocks based on vibration were pendulum clocks. So anecdotally, I don't know, this is linked to Galileo. So this is the gentleman up there. I think I can also. Oops, no, can I not? Is this a? I don't want to write. Anyways, let's leave it like that. So the gentleman on the top left, this is Galileo, and he was visiting a church, and Catholic church in Italy. So they have this incense. What is it? Incense. All right. Weihrauch in German. Holders, and the priests in their ceremonies, they kind of like swing that. And while observing this, I mean, this is somehow hooked to the wall. I don't know why this is in this fresco there. But while observing this motion, Galileo thought that realized that the motion of this holder is the period of the motion is constant, and this inspired then clockmakers to use a similar construction, the pendulum, to make clocks. So this is the ancient clocks here in, I don't know, I think this is probably 15th century or something like that. There's a gentleman called Huygens, a Dutch physicist, astronomer, they did everything there. Physicist, he built clocks, for example. That was a very lucrative business back then because it was prestigious to have a clock at home back then. But also, I mean, you need to have, I mean, timekeeping is very important to keep. I mean, you came here on time. Without a clock, that will be difficult. Clocks are important back then. With navigation was a big thing. So if you ferry now on a ship, you're trying to go from Spain and try to get to India or whatever you're doing. you need to navigate. And of course you can use the sun for navigation. Sun is okay if you want to determine how much north or east you are, but in terms of east-west it's a little more difficult. So you can use the stars. Stars is okay, it can be very precise, but you need to know the stars, of course, and if it's cloudy, you're out of luck. So another way is to use clocks for navigation, and that was one thing the Europeans invented or like the Chinese actually. I think the Chinese, anybody knows about Chinese history? I think they invented the clock earlier, if I'm not mistaken, the mechanical one. But I never made it on ships or so far as I know. And of course, here on the left-hand side, I'm from Germany, so this is the Google clock. That's my watch at home, my personal watch. No, not really, but so pendulums. I mean, this is just we're going to discuss the pendulum probably maybe next lecture or the lecture after. So this is just a vibration par excellence. So after the pendulum, so the nurse, I mean, there are a lot of iterations there, what to use for timekeeping, but one has resorted for a long time to quartz clocks. So this is an this oscillation has electric components and mechanical components, so it's a combination there. Back when I was younger, we didn't have phones, so we usually had a quartz. You always have. I don't have a watch right now because I'm just looking at my phone. But when I was younger, it was usually to have a quartz watch to kind of keep track of the time, whatever you need to show up at 4 p.m. to lecture, or 2 p.m. for office hours, or whatever, 6 p.m. for dinner, and. So this is the chips here they use on the left hand side for this quartz for timekeeping, and things have advanced, and what the most timekeeping or the most precise timekeeping now is done by atomic clocks, and they use like certain ground states from a certain cesium isotope, and those ground states they emit by jumping between these ground states. Cesium emits a certain particle with a certain frequency, and they use this frequency to define time. So the SI units, they have the standardization NIST. They have I think 9 units, physical units. These are the defined the standardized units. And they use the oscillations essentially there to define time, which is a very basic unit. And timekeeping you need for a lot of things. I mean, for the internet, you need to send timestamps across the globe to enable communications. You need timekeeping for GPS, because you kind of stop the distance your signal is traveling to the satellite to triangulate your position. So timekeeping is a very important business, and all relies on vibrations in some sense. Oops. The Earth. I mean, we've discussed that structures are, or like we've seen that bridges are not the most static buildings, but that certainly also holds for the Earth itself. We all have heard about earthquakes. I think this up here to the left is Alaska. I think in the 50s or so. It's a little older. But I mean earthquakes. You've seen the news. I think I do have a video, but I mean you can picture what an earthquake is. I mean I assume Wisconsin. I haven't checked, but I assume Wisconsin is not too. This is an earthquake if it loads. So Wisconsin, I guess.
A powerful 6.1 magnitude earthquake hit Taiwan, sending people fleeing. The quake shook shops and damaged buildings, lasting for about 10 seconds. Watch as everything in this clothing store swings from side to side. The earthquake also caused panic at this busy train station,
I guess here
forcing
not so
commuters
much.
to run for the
California
exits.
more. Again,
Subway service
anybody
was
has
suspended in the capital
experience
city
with
of
those kind
Taipei.
of phenomena in where they grew up, or
Journalists at this local TV channel
see
whipped out their
something,
phones
somebody
to
nodding,
capture the
so,
tremors. Watch as the lights in their office swing.
So buildings, there are codes out there, standards, especially for California and Japan. They're very rigorous or meticulous that these standards should be upheld. And the standards are there to kind of say that this building is earthquake proof up to a certain threshold, of course. Of course, then there are another thing which you can think about the Earth is tsunamis. So tsunamis, I think the big one there was just I think 20 years ago or even more, there was a big one in Southeast Asia, caused a lot of, which kind of initiated to update the tsunami warning in there. And what those things do, the tsunami warning system, they have a bunch of sensors on the Earth's on the ocean ground, and they measure the pressure, and the pressure gives you an idea of how deep the water is. And of course, if the water the pressure is less, then there's less water on top of it, and if the pressure is higher, it's like kind of a weight, the water column is higher. And so that's a way to kind of measure waves. And now these sensors are conditioned to look for very specific wave patterns, so very specific oscillation pattern or vibration pattern again. And if this is there, it sends out a warning, and then hopefully the sirens go on the beach you're at, or hopefully not at, to alert the people there that they should evacuate the area. Similarly, there is a very sensitive. So the Earth is monitored very well, especially in the areas where you might expect earthquakes. So here it's Japan, China, along Indonesia, also here in the US here, and those kind of those seismometers, they detect the movement of the Earth very precisely. And you might think this is for scientific reason. By now it's primarily for scientific reasons, but it was actually started back in the days, probably 50s, 60s, due to the Cold War. And probably later, I think 70s or sometime, there was, and why was this built, those kind of monitor stations? I'm pretty sure there's something up here in yeah, this is Iceland maybe. Alaska, very important, this is for the US to monitor Russia. Because back in the days when they did atomic bomb testing, if you have a sensitive enough instrument, you can detect if the Russians did something, and the Americans, of course, wanted to detect, hey, did this guy do some testing? And essentially, at some point there was an agreement, the Americans and the Russians, and I don't know if anybody else was involved back then, and said, hey, we're not going to do any testing anymore, because it's obviously not good for the environment. Of course, you can believe your party, you can believe them, or you can believe it, or you better check if the partner you signed in the treaty is actually upholding the treaty. And that's why the seismic monitors are developed primarily in these days. And now they are more for, of course, earthquake warning, but also for scientific studies. So this is, for example, the one. There was a rock slide somewhere in Greenland, and it just knocked a bunch of rocks and ice and whatever into a fjord. And you could see a certain frequency of a wave, so essentially a vibration of the Earth crust, certain frequency for 9 days. You can measure that with this kind of instruments across the whole globe. So somebody gave like this, the rock slide was large enough to give a large impact that we can like kind of sensor the very sensitive instruments across the whole globe. So essentially the whole globe is vibrating if we have a rock slide big enough. This also kind of here on the left-hand side also tells you that the whole Earth is vibrating, because what happens, so what this is sometimes, in some sense, the vibration intensity of all these instruments. And what this research has showed, or what this graphic shows, is the line here is when the shutdown during COVID was instated. And you could see by the level that drastically the vibration amplitude of the Earth dropped just because people were not moving that much. Traffic was stopping and all those things. And you can relate it very well. And another thing here, what they say, I don't know if you can read that, the other blue line there is Christmas. Because during Christmas also a lot of operations stop, a lot of people don't go to work, maybe less travel, it's debatable. But you can always see also like kind of a Christmas drop, which is also interesting, at least in certain geographic locations. So the Earth is vibrating, and we are on the Earth, so we might as well study it. Other applications, structural health monitoring. So the vibration behavior of a structure is very sensitive to changes of the structure. So if you have a vibrating structure and something happens to it, changes, then the vibrations change. So now if you can detect those changes in the vibration, you can alert whomever is interested in that to, hey, your structure is changing, you might want to check out, maybe do some maintenance or something. So this is one application. This can be done, is a big topic in structural engineering, so buildings, bridges, and so on, as you see there on the left-hand side. But it can also be done on much smaller scales, electronics in some sense. Energy harvesting is also a topic. This is a research area still, where we kind of like, we do see vibrations like they happen all over us, and so they kind of want to convert whatever is exciting this a beam. Essentially, there are piezoelectrics. Anybody knows piezoelectric effect? So to people, so a little bit. Let's say this is a structure, this is an energy harvester, and whatever you have environment that acts here, and this kind of deforms the beam. And there are certain ceramics, if they are deformed, they produce current. And you can then connect electric circuitry to kind of harvest the energy, or the current which is produced. With the current, you use the current and you get so you kind of like convert the electric energy then, or like you harvest electric energy from the piezo. So from the voltage drop, you get a current, and then you can harvest the energy essentially. So these are special ceramics essentially, and this can happen in many there are many applications for that. So you can think about on a ship, for example, if your ship is moving constantly due to the waves, you can just put your harvester on the ship, and then because the base is moving, the whole thing might deform, and you can harvest this energy essentially. So the power is usually not that high, so you're not going to power your ship with that, but you might run a light or some sort of sensor on that. So this is an application there. Similar, you can think about, okay, now I told you how the wind is maybe very detrimental to bridges. I've shown you one example. But you can also think of using this wind-induced vibrations in your bridge structure to harvest energy, to power a sensor or something like that. Another thing, material characterizations, for example. So atomic force microscopy. So what they do, this is the beam. So this is the atomic force microscopy. Relies on the beam with a certain tip here, and there are certain operation principles how to operate an atomic force microscope. But in one of them, they drive the beam here. So they drive it again, and now the operating principle is now that the tip here is brought very close to the surface you kind of want to investigate. And due to the closeness of the tip and the surface you want to investigate, there's going to be some sort of interaction. And this interaction is going to change the vibration pattern of this beam. And so by measuring the change in the vibration pattern of the beam, you can relate then this back to certain changes of the underlying structure properties. So you get like, for example, here like a height diagram or something like that. Similarly, here 3D printing, you have a lot of, they have a lot of vibration problems because the 3D printer is usually a printer that moves around. And I don't know if you guys, I'm not too familiar with 3D printing. I have actually never printed with 3D print myself. Anybody? 3D printing, guys? Oh, let's see. I was told that the problem is that the surface finishes, you can see like these wiggles. I don't know if that is anybody, so I see some nodding there. So that can happen, that this could be a resonant effect again of the printer moving. And there are certain control schemes there which can alleviate that to some extent. So this is another application where vibrations might show up. So I've talked a lot about vibrations. Anybody has any idea about vibrations in their everyday life or research, or I don't know, anybody inspired by any application here? Anybody is doing research with vibrations or other coursework vibrations? Yeah?
My research is in like acoustics with folk sound, and also doing it as well.
Yeah. So is this? Do you know if the thing is working in was it tapping?
I'm doing it to get material properties involved in after using it with folk sound and like disrupting the knowledge of the kind of a different application for that.
Yeah, but I mean, you can also get material properties from that, but the thing needs to be operated. I think it's the tapping mode. You can operate those things in different conditions. I'm not sure. But good that you mentioned it. I think I actually do have a. Yeah, I somehow I skipped this slide. So acoustics, big topic. So sound, everything which is producing sound, or a lot of things that are producing sound, is underlying from vibrations. So sound waves is essentially a vibration, and so you might have the pleasant effect is of course, or can be music. So we can see, for example, here, this is the violin string here. Good. Are you playing? Yeah, it's very slow-mo. So this guy is now, or a lady, I don't know. They are moving the bow across the string, and you can see that the thing is now vibrating. So it's moving left and right. And this then creates a sound. You can hear whoever is playing this instrument. Just by the way, this is still a research topic how this actually happens, because the contact here between the bow and the string is very hard to model. And I think not this year, but a year back, I was in a conference and somebody was talking about that, how to model that and so on. So it might be look very simple, but it's a very hard topic to actually understand what's going on there. Yeah.
Is the vibration there caused by like repeated slipping?
Mm-hmm. Yeah. So that's of course. So yeah, you kind of, it looks. I mean, when you like see the person doing it, looks kind of continuous. But if you zoom in, of course, you have stick and slip along the surface in some sense, and this then creates the vibration. But it's of course, how do you model this stick and slip? It is very, very tricky. It's not so easy. So this is the another thing in terms of sound I always like to show, because I'm German. Oh no, we need to go here. Brake squeal. There we go. Now we have to. Tell you, I don't drive this car. I don't know about you guys.
Few sounds resonate more with a Porsche enthusiast than the adrenaline-inducing rumble of a high-performance engine, or the G-force-generated release of maximum torque. Yet, there is one decibel-driven disturbance that has been misunderstood for far too long. Brake squeal. Brake squeal occurs when the energy of motion is converted into heat and minute vibrations, which then
So under certain conditions, people like report that when they brake, they hear a certain sound, the squealing. And this is, of course, if you want to sell a car, which is, I don't know how much this car is, probably a couple of $100,000. I don't know, over here can go up to $1 million probably, or even more. You kind of want to avoid that, but it's generally like it's an unpleasant sound, makes you unsafe, so you feel unsafe. It's not necessarily a safety issue, but it's a comfort issue essentially.
Debate throughout the brake
And this
system.
can be
noise
again
is often mistaken for a malfunction.
understood as
However, that is rarely the case.
kind of an impact between stick and
Brake
slip.
squeal
between the
is the result of a
brake pad
condition called
and
stick slip,
the surface is
causing
breaking off, so
microscopic
you have the brake
vibrations
pad.
that create noise
And
to be
this is
broadcast by the brake
the
rotor,
other part is
which
rubbing
acts
on,
as a
I don't know what this is
speaker.
called. And you can see
Necessity
that
dictates that the Porsche brake system
there's an
be designed
interaction
with
which then
large rotors and
resonates
pads.
with the whole
Due to the larger
with the
pad
whole
surfaces, pad pressure distribution can vary when
blade
the brakes are
disc,
applied at low
essentially.
speeds,
And
increasing the
this
propensity for
structure
brake
as
squeal.
it is acts essentially
Vibrations that create
here
noise
as a loudspeaker.
to be broadcast by the brake rotor,
You can
which
see that
acts
here
as a
in the
speaker.
animation, so yeah, there it's
This-
no, wait. It's too much. No, it's too much. You see in the animation where the sound waves essentially traverse from the disc of the brake, essentially. And if you want to design a well-selling car, you kind of want to avoid that. All right, I think good that you mentioned acoustics. So I'm gonna go to the course schedule, not today. I'm gonna do that later. I think I've talked a lot today. Just general expectation. I mean, I think that goes without saying a lot. I just wanted to mention it. Treat yourself, everybody involved, with respect. If you need to leave early, you can do that, of course. Make sure not to make much noise. If you know you need to leave early, maybe sit next to the door, something like that. I mentioned about submitting homeworks and so on. If you have any accommodations or you see that religious holidays or other things are upcoming, talk to me as soon as possible so we can accommodate things, so we can work with you that you are on track in this course. Yeah, I think with that, I upload the slides and the recordings at some point. And yeah, enjoy the course, bring positive vibes, and yeah, thanks for listening.